Now, if you've been keeping an eye on the website, I thought I had published what I wanted to cover today on the website, but when I checked there a moment ago, it wasn't published. So I've just updated it literally seconds ago. And if you do go to the website now, which you don't really need to, you can follow me on the screen. But this is what the website looks like. So these are the two new cards that I want to get through. I'll get through this one today. I'll start off this one today as well, but I certainly won't get through all of it. And so we're moving now into the AWS part of this module, which is where we're going to be deploying our web API, the back end, if you like, of our web application. So first thing I want to look at is something called the CDK. And we will be using the CDK right throughout the first half of this module. So as usual, there's a set of slides and a lab, which you'll be able to get through today, or sorry, this week. So let's work my way through the slides. So when you're developing any server-side functionality today, and if you want to deploy that functionality in the cloud, then that means you need to create or provision, to use the correct term, you need to provision some infrastructure in the cloud for your application. That could be a mixture of compute infrastructure, storage infrastructure, database infrastructure, messaging infrastructure. All of these are the types of resources or infrastructure that we want to create in the cloud. And so how do we do it? Do we have to do it manually somehow? Hopefully not. Or can we automate it? And the answer is we can automate it today anyway. We can automate it. And one way of doing that is on the AWS platform is to use this Cloud Development Kit or CDK to automate the provisioning of the infrastructure that you require for your application. The application in our case is a web API. So the context for this CDK, our goal is we want to be able to provision and configure infrastructure, but we want to be able to do it in a way that is consistent, in the sense that if we want to do it multiple times, then we get the exact same result every time. That's what we mean by consistency. Why should we want to provision our infrastructure many times? Well, one reason might be that we want to have both a development environment and a test environment and a prod environment. So these are essentially three different environments, and each of them we will have to provision the infrastructure for. And obviously the infrastructure should be the exact same for all three of them. Otherwise there's no point. So that's one reason for needing consistency in the way we provision our infrastructure. Also here, I'm talking about, this is kind of AWS specific, but the AWS platform is a global platform. I just checked there a moment ago, the AWS cloud is globally split up into 33 different regions. When we deploy an application in the cloud, in the AWS cloud, we have to specify which region we want to deploy it to. Now, you may actually want to deploy your application to multiple regions, depending on where your user base is. So if we've got a heavy user base in Europe and we've got a heavy user base in, let's say, Asia, then we might want to actually deploy our infrastructure or our application into both of those regions. Hence, we need to configure or provision the infrastructure in both of those regions or multiple regions. And again, we want to make sure we have the exact same infrastructure configuration in each region. Hence, it needs to be, the way we do it needs to be consistent. Clearly, provisioning infrastructure using a manual approach is the opposite of consistency because it's very error prone. If it's a human process, it's error prone. So we don't like to approach this in a manual way. And we don't like it because it lacks consistency. Also, I'm saying here, we don't have a single source of truth. This is a term that we use quite a bit in software engineering. Now, if we did have to do it manually, then one way we might try and achieve consistency is by documenting the steps that you have to go through to provision the infrastructure. And that might work okay if you've got a really good documentation describing the steps. And if you only have to provision the infrastructure once, albeit in multiple regions and on multiple environments, and that infrastructure never changed, then a manual approach might work, as long as you've got it very well documented. So the document is your single source of truth, but more than likely the infrastructure is going to change over time. And so, okay, you may edit your document, but that it just starts getting messy. The documentation may not be up to date. There may be multiple copies of it, etc., etc. So we certainly don't like the manual approach. What we would like to do is to automate the provisioning of the infrastructure. And that really translates into somehow writing the automation using code, or the automation steps, implementing them in code. And so the beauty of code is every time you run it, it does the exact same thing every time. So if we could somehow implement the provisioning of our infrastructure as code, then we would have a certainly much more consistent provisioning process than we would using a manual approach. So enter our infrastructure as code concept, which I'm sure you've heard of before. And so just to repeat, so the infrastructure code idea is it allows an organization to automate and manage the provisioning and configuration of cloud infrastructure in a consistent way. Now, just because maybe there are some of you who haven't done very little or maybe no cloud stuff before, what we provision, when I talk about infrastructure, the infrastructure is comprised of resources. This is the terminology that we use. So the kind of resources that we might want to provision on the AWS platform anyway is we might want to provision an EC2 instance. That's essentially a virtual machine. We might want to provision an S3 bucket. S3 is Amazon's kind of file stroke object storage service. And we talk about creating buckets. A bucket is a bit like a folder, I suppose. We might want to provision a database. There are many database services provided by Amazon. DynamoDB is one of them. That's the one we use. But we might want to provision some sort of queuing or messaging infrastructure, for example, using an SQS service. So these are all examples of what I'm calling resources. The resources make up our infrastructure. So the benefit of this infrastructure as code approach is that, well, if it's code, then we can use tools like Git and GitHub to apply version control over the evolution of our code. And we all know the benefits of using tools like version control tools on our code. It allows us to see what parts of the code has changed. If in case we introduce bugs in our infrastructure code, we can track what changes have been made to the code to try and identify when was the bug introduced. We have got our single source of truth now because our single source of truth is the actual version control repository. Let's say a GitHub repository, and everybody can have access to that. And also GitHub, is a way of sharing essentially sharing good practices, best practices in any form of coding, whether it be infrastructure coding or application coding. So all the benefits that we get from version control in the software world, we can now avail of those in our infrastructure creation as well, our infrastructure provisioning. I always like to see what's the history of this, any topic that we talk about. I don't know if you find it interesting or not, but if we just kind of track in very high level terms how this infrastructure as code has evolved over time. The very first approach to it was a scripting approach. So what you did was you wrote a script. Typically, Python was probably the most popular scripting language that was being used. So this is a Python script. And what the Python script does is it sends requests to your various AWS services. So on the right here, I've got my AWS services, and the services are what manage your infrastructure resources. So the script would send requests to the various AWS services that it was interested in, essentially requesting the service to create a particular resource for it. So that was fine. That was our code. So we had to learn how to communicate with these services. That was fine. The docs were there to allow us to do that. And so when you ran your script, it sent the requests to each of the relevant services to create the resources that we needed, our infrastructure resources. That was okay, but as a first effort, but there were all of these problems associated with it. So number one, what happens if an API call fails? So my script here now is going to be making requests over the web API. This is what we mean by API requests to the various services. So it might send a request to the EC2 service to create an EC2 instance. Later on in the script, it sends a request to the S3 service to create an S3 bucket. Let's suppose that request, for whatever reason, networking or whatever, or availability of the S3 service, let's suppose that request failed. Where are we now? Our program crashes, let's say. We now have some resources. Some of the resources have been created, but the rest of them haven't. So we kind of have to go back and undo the work that has been done by the part of the script that has run successfully so far and start all over again. So clearly that's very messy. Let's suppose our script works successfully and it creates our infrastructure, and later on then we want to make some changes to the infrastructure. So we essentially have to write a completely new script to describe the changes that we want to make. The original script is no longer of any use to us. So that's we finish up. It would probably be quicker to do everything manually at this stage rather than using the scripting approach. Also, maybe in part of your script is dependent on the earlier part of the script having successfully created the resource, and the resource that was created is now ready to receive requests. Maybe later on in the script, you want to send some requests to a resource that was created earlier on. But how do you know in your code whether the resource its creation is completed by AWS on the cloud side? There was no easy way of checking that. And the last thing I'm mentioning is about doing rollback, which is, again, kind of linked to the idea that if part of your script worked successfully, but the rest of it didn't, how do you kind of roll back to an earlier state? So lots of problems associated with that scripting approach. Then the cloud providers, and let's just focus in on AWS. AWS provided what's called a resource provisioning engine, which was essentially another service specifically for this whole infrastructure as code objective. And the way the resource provisioning engine worked, in the case of AWS, the resource provisioning engine is a service called AWS CloudFormation. Now, what you did as a developer was you wrote what was called a CloudFormation template, either in JSON or in YAML. And those of you that did the cloud architecture module in the previous semester would be familiar with this. And this CloudFormation template, this JSON document, essentially describes in a declarative way the infrastructure that you want the cloud to create for you. And you obviously followed the rules and regulations, the documentation that came with the CloudFormation service as to how you describe the infrastructure that you need. So you wrote your CloudFormation template. This is your code now in this case. And you gave that template, you uploaded it to the CloudFormation service, and it took care of making the API calls to the various other services. So whereas in the previous screen, our Python script was communicating with the various services, now CloudFormation is taking care of all of that heavy lifting for you. And it also took care of if there were failures, if a particular request failed, then it would retry it a couple of times and all of that. Then if you wanted to make a change to the infrastructure, change a particular piece of configuration or add some new infrastructure or remove some part of the infrastructure, what you did was you went to your CloudFormation template and you made the necessary changes there. So your CloudFormation always describes what state you want your infrastructure to be in. State means what are the various parts of the infrastructure, what are the various resources, and what is the configuration of each of those resources. So simply by updating the template to now describe the new state of your infrastructure that you desire, you then send that new version of your template up the CloudFormation, and it took care of working out what requests it had to make to which services to make changes to the resources that have been provisioned for you. So CloudFormation took care of working out how do we get from the current state of our infrastructure to the new state as described by this new version of the template that has been updated to me. And that all worked brilliantly. And CloudFormation is still core to this whole infrastructure as code idea in AWS, except we no longer write these CloudFormation templates, as we'll see. So the advantages of the CloudFormation, which is a resource provisioning engine, as in it provisions resources for you. It was very easy to update your infrastructure. You simply updated your template, and it was very reproducible. So you could run, you could write your first version of your template and ask upload it to the CloudFormation service in region 1, updated it to region 2, 3, and 4, and you now have multiple copies of your infrastructure across multiple regions. You could also associate it with different environments. To update the infrastructure, and in each region, you just make one change. You just change your template and upload it to the resource provisioning engine on each of the regions, and it took care of all of that for you. The downside of this approach is that the syntax, because what you're essentially your template here is either written in JSON and YAML or YAML. And neither of them are really that nice to program in. We're referring to them as code, as programming, but it's at best, it's declarative programming. It's certainly not procedural programming, which is what we're much more familiar with. So the syntax was verbose and difficult to read and maintain. Also, I'm saying down here that there were no abstractions available to us in this templating environment. Abstractions are what we live by really in programming. Abstractions would be things like classes, libraries, all that kind of stuff. Without classes and libraries, procedural programming would be pretty much an impossibility. but we do have abstractions. So that's what makes modern day programming a lot easier than it would be if we didn't have them. But in the templating, in the CloudFormation templating world, we don't have abstractions. Also, we don't have any kind of default values that might be assigned to various configuration settings. We had to be specific about the configuration settings for each part of a particular resource. I'm just going back now again. It's kind of starting all over again in terms of plotting this infrastructure as code journey. So at the beginning, AWS had a number of services, and really at the beginning, the only way we could create infrastructure is by using what's called the management console. The management console is this, right? You actually had to use this is just a web interface to the AWS cloud, and you could go into each particular service. So if I wanted to go into the DynamoDB service, I'd go DynamoDB, go into that service, and create a table for myself and step my way through it. But it's stepping through forms and filling out fields and clicking and all this kind of stuff, right? So that's all that was available to us at the very beginning. So we had no infrastructure as code approach at the very beginning. In order to facilitate infrastructure as code, and we know the first generation was the scripting approach, what AWS did was they provided web API interfaces to each of the services. And so that's what allowed scripting to be possible. Okay. The next thing they did was, but the web APIs, the way we communicated with the services via the web APIs was by just sending raw HTTP requests to the web APIs. And clearly, that's not great. The next thing they did was they provided an SDK, software development kit. Here, they provided an SDK, and the SDK took care of the low-level HTTP communication with the web API. And then we imported the SDK into our source code, and we used the SDK to implement our infrastructure as code. And that's really where our Python scripting began. Very few people were using just the raw web API interfaces to the cloud services. After the SDK, then CloudFormation came into the picture. So I'm saying all on the left here that CloudFormation is around 2011, whereas the AWS platform itself dates back to around 2005, 2006. So, about roughly 5 or 6 years after the beginning of AWS platform. It's only then that the CloudFormation service became available. And what the CloudFormation does for us is it manages the state of your infrastructure. That's why I'm highlighting state here in this diagram on the right. By state, we mean what are the various resources that make up your infrastructure, and what are the configuration settings for each of those resources. That constitutes the state. To change the state of your infrastructure means adding new resources and or changing the configuration of existing resources. But all you had to do was, in your CloudFormation templates, was describe the new state, and CloudFormation worked out how it transitioned your infrastructure from the current state to the new state. Yeah, CloudFormation took care of that by communicating. CloudFormation actually uses the SDKs to communicate with the web APIs to communicate with the services. So it's still using this stack, if you like, behind the scenes. At the very bottom here, I'm mentioning something called Terraform. Terraform is an alternative to CloudFormation templates. It's a very popular alternative, as it turns out, in the industry. The other thing about Terraform is that it's also a templating language. but it's not as verbose as CloudFormation templating, and also it actually, you can use it for different cloud providers. So whether you're using Google Cloud, Microsoft Azure, or AWS, you can use these Terraform templating language for configuring those other platforms as well. Enter the CDK. So the CDK now is kind of wrapped, it's a wrapper, if you like, for CloudFormation. And whereas in CloudFormation, you describe your infrastructure using a declarative programming language, i.e. JSON or YAML. With the CDK, you describe your infrastructure using an imperative programming language. And there are many languages currently being supported by the CDK. We will be using TypeScript. But you can see in the right there that there are a number of other languages. It hasn't been around that long. It first came out in 2019. Well, okay, that's probably 5 years now at this stage, but really maybe only in the last 3 or so years that it has started to become quite popular. There's still a lot of software houses still use CloudFormation. There's also quite a lot that use Terraform. So I'm not suggesting that the CDK now is dominating the infrastructure as code. CDK is specific to AWS, by the way. It doesn't work with the other cloud providers. I'm not suggesting that the CDK it has completely taken over from the other approaches, but it is still arguably very popular and growing in popularity. And the main thing it has is this ability to describe your infrastructure using an imperative programming language. And as developers, we're far more familiar with imperative programming than we are with declarative programming. The CDK provides a very large class library, and it's these class libraries that contain the types of abstractions that are lacking in CloudFormation. And also these class libraries take care of assigning default values to various settings for resources, so that you don't have to in your code. So by using these class libraries that come with the CDK framework, it really means as a developer, your experience in creating infrastructure code is a far more pleasant experience than writing CloudFormation templates. Because the IDEs that you will be using VS Code, but the IDEs, provide the types of help that IDEs do, which includes hinting and IntelliSense. And we saw that when we were using just TypeScript. Also, the actual volume of code that you write is far less. So I'm saying here, CloudFormation templates tend to be much longer in terms of a line of code count than your CDK code. You can also do things like automate the testing of your infrastructure, which we won't go near. We won't have time for that. So we are going to be using the CDK for the first half of this module. And so to some of the concepts, well, whenever you're developing any software, you're talking about creating an application. So we use the word application here as well in the context of the CDK, even though we tend to associate the word application with functionality, but we're not necessarily dealing with functionality here. We're dealing with infrastructure creation, but we still have this notion of an application. So we write a CDK application, and a CDK application contains one or more stacks. We will only have applications that consist of one stack. A stack is comprised of many constructs, and a construct will eventually cause the creation of many resources within your AWS account. So there's a one-to-many relationship from left to right here. So we will be writing constructs, which are really just creating instances of classes and passing parameters to those instances. But each construct instance in our code, when it eventually gets translated into CloudFormation, because that is actually what happens, whereas we write our infrastructure using an imperative programming language, TypeScript in our case, but that TypeScript code has to be converted into a CloudFormation template, because clearly CloudFormation doesn't understand TypeScript code or any other imperative programming language. It only understands CloudFormation templates, and we still are going to be using the CloudFormation service to create our infrastructure for us. But the CDK code that we write in TypeScript in our case, it's going to be compiled, if you like, or the term we really use is synthesized. It's going to be synthesized into CloudFormation template code, and then that is given to the CloudFormation service, and it does the rest. The unit of deployment in this CDK world is a stack, which in fact is the same term that we use if you have done any CloudFormation stuff, i.e. if you did the module in the previous semester, you'd have come across this term of a CloudFormation stack. So that term is reused in this world. Doesn't matter if you haven't done any CloudFormation. Just by way of a simple example, on the left, we have just some CDK code, and we'll look at it in detail later on, but just all I want to get across here is this idea that the developer's productivity is much greater when you write CDK code as opposed to CloudFormation templates, simply because you have to write less code. But if you want to, for example, provision an EC2 instance as a resource as part of your infrastructure, on the left, I'm showing you how you would implement it in CDK, and it roughly comes to about 12 lines of code. And that 12 lines of code gets converted into a CloudFormation template. It kind of balloons up to about 150 lines of code. Maybe that's slightly exaggerated now, but you're talking about almost 10x difference in the amount of code that you have to write. Okay, we do a lot of cutting and pasting, obviously, but it also means that your CloudFormation template is physically just a much larger file. So if you are reading somebody else's CloudFormation, it's always going to take you a lot longer to read through the code than it would to read through the code on the left there. So this is the kind of when we talk about running a CDK application, the net result we want to have is a set of resources are created up on the cloud for us. So this is the kind of execution flow. We, as a developer, we write our infrastructure as code using an imperative programming language. So our infrastructure is described in an imperative language. We give that to the CDK framework, and it generates the CloudFormation template from it. And then from then on, really, is what was happening back in the earlier years, I suppose, in the infrastructure as code journey. The CloudFormation template was given to the CloudFormation service, uploaded to the CloudFormation service, and it took care then of communicating with the relevant AWS services. So this is the kind of SDK calls being made here by CloudFormation, requesting the service to create a resource or resources for it. So the service then created the particular resource, and a collection of resources were linked to a stack. Mind you, that's only in CloudFormation's world. The resources, as far as they're concerned, they're just completely independent of one another. But from CloudFormation's point of view, a collection of resources are somehow part of a stack. And an application back here, your application might comprise of many stacks. Although, as I said, we will only have a single stack app in our case. In terms of using the CDK framework, it comes with a CLI as well, command line interface. So the steps typically are you create an empty, well, sorry, you create an initial CDK app using this command here. You do have to tell it what language you're going to be using to implement your infrastructure code. And then it scaffolds up a folder structure for you. You then go into a particular part of that folder structure and implement your infrastructure code. In other words, you develop your stacks. Now, optionally, you can run this command from the command line, and what that does is it gives you a local copy of the CloudFormation equivalent of the imperative code that you've written up here. Here's the really important step, though. The CDK deploy is where the CloudFormation template that was generated by the CDK is uploaded to the CloudFormation service, and it does all of the rest. It takes care of all the communicating with the various services, etc., etc. Then maybe later on, you might want to make some changes to your infrastructure code. So you're kind of back to changing the code back here. But you make changes to the code and you do CDK deploy again, exact same command. But this time the CDK deploy is going to create a new CloudFormation template, and it'll upload that template to CloudFormation service. But the CloudFormation service knows now this is not a new deployment. This is essentially an update to an existing deployment. And as I've indicated before, what it will do now is compare the new state of the infrastructure that's been described by this new CloudFormation service, CloudFormation template, compare it to the current state and work out what requests it needs to send to the various AWS services in order to update your infrastructure. Eventually, you might want to actually tear down your stacks, destroy all your stacks, i.e. destroy all your resources. And so just CDK destroy will do that. So, but really what you're doing here in this command is you're sending a request to CloudFormation and telling it to deploy the stacks that make up your app. And again, CloudFormation is going to communicate with each of the services that contain a resource that's part of your app, telling it to destroy a particular resource. When you do the CDK init, it creates a folder structure that you see on the right there. There are really only two files and in fact only one file that you will find yourself putting code into. But the two most important files are this one and this one. In the bin file, I'm saying here on the left, it's the entry point for the framework. So when you want to run your app, and by running your app, I'm talking about, this kind of process here, triggering this process. When you want to run the app, the CDK framework goes looking for the particular app file in your bin directory. And inside that app file, there's typically only a couple of lines of code. It will indicate what are the various stacks that make up your app. And that's about it, really. Then in the lib folder, you will typically there have one file per stack. And inside in each of those files, there is the full infrastructure code for that stack. We won't really be doing any of the testing stuff that I'm mentioning down here. Now, inside in the stack files that you have in the lib folder, you're writing code. And essentially what you're doing is you're creating what we just, I know it's a very general term, but we create construct instances. And a construct is really a class, right? We create construct instances. And there are three types of constructs available in the CDK framework: L1 constructs, L2 constructs, and L3 constructs. the vast majority of what we will be doing is creating what are called L2 constructs. And this is now a kind of reflection of the advantage of writing infrastructure code using an imperative programming language with the benefits of abstractions and default values for configuration settings. When you create an L2 construct inside your infrastructure code, that construct is going to materialize as multiple resources in your CloudFormation template. So there's a kind of one-to-many relationship between an L2 construct and a CloudFormation resource. Which is why we've got this, which is why we write far less CDK code. So there's a one-to-many relationship between your CF there is CloudFormation resource and your L2 construct. You also have the advantages of, there's lots of default configuration value settings available to you in these L2 constructs, which means you don't have to be specific about them. An L1 construct is different. In L1 construct, there's a one-to-one relationship. So, if you had 5 L1 constructs in your CDK stack code, then that would translate into 5 CloudFormation resources in your CloudFormation template. So you're not getting a whole lot from CDK if you were using a lot of L1 constructs. But we don't tend to use any of them, or very, very few of them. L3 constructs are a level up again from L2, and again, you've got a one-to-many relationship, but L3 constructs tend to implement well-defined patterns of infrastructure, which we won't get a chance to look at. A lot of talk. Let's look at something practical. So here, do I have it? Okay. So I've ran CDK in it, and I've created a TypeScript CDK project for myself. And I have, here's the structure that I was talking about. And really the only file we're interested in is this one here. And all I want to do in this app is I want to create an EC2 instance. Yeah, that's it. That's my infrastructure. Okay, so I've got a few. Well, first thing I should say is that this is a essentially it's a node project. So I do have a package.json, you can see here. And it has some dependencies that you'd expect, like, the CDK. The CDK, I suppose you could say that's the CDK L2 construct library. And this is a kind of higher level construct library again, but this is the main one. This is the one that contains the various L2 constructs that we can now use in our infrastructure code. And the dev dependencies relate more to TypeScript, and we're also including some TypeScript declaration files, these .d.ts files that will be useful to us for hinting and IntelliSense and all that. But the main one really is this one here, and this one, in fairness, if you need both of them. So you got to run npm install, obviously. And then if we go back now to our, what I'm going to call our stack file, whereas this one up here is our app file. I'll look at that in a second. And so I'm importing so the CDK library that I showed you there in the package.json. There are only parts of it that you might need in a particular app. So in this one, I only need the EC2 part, the EC2 part of that library. You can see here, I'm just referring to one particular part of it. So I'm importing that, and I have to import the construct library as well. So to implement a stack, you have to, to implement the stack, you've got to create a class, a TypeScript class that extends the CDK stack class. And really, it's only the constructor that you implement. You don't tend to have other methods that you need to implement of this stack class. And it's in the constructor is where you put your infrastructure code. So if we walk through it, even though it's quite short. Let's just ignore that line for a second. Here's where I'm creating my EC2 instance, or I'm requesting the creation of an EC2 instance up in the cloud for myself. And so I'm using a method called instance from my CDK. Sorry, I'm creating an instance, which is part of the EC2 part of the CDK library. And instance here is an example of an L2 construct. And the parameters to this instance that I'm creating are, I have to tell it what stack I want to link this instance to. And so clearly I'm going to link it to the containing stack. This is just a name that you want to give to the instance. And the rest then is configuration settings for this instance, or the ones that I want to be specific about. There are other settings, but I'm accepting the default values for those other settings. And in fact, some of the settings that I'm being specific about, I could probably have left them, use the default values as well. To go back to this line here, when you create an AWS account, again, the people that did the module last semester now would be familiar with this, but when you create an AWS account for yourself, automatically a private network is created for you up on the AWS cloud, or what's referred to as a virtual private cloud is created for you. So you get one virtual private cloud or one private network created for you by default. You can create other ones, but what we want to do is we want to launch our EC2 instance, and we want to launch it in the default VPC that has been created for us. So here, all I'm doing really is just I'm asking the VPC service to give me a reference to the default VPC that has been created for me. And I'm linking that then. Here I'm linking, is that the line? Sorry, this line here. I am essentially locating my EC2 instance in that network or in that VPC. The other settings then are, really what I want to do is I want the EC2 instance, which is really a VM, virtual machine instance. I want it to be a Linux server for me. And so that's really what I'm kind of getting at here. That's what I'm getting at here, right? Kind of telling it that I wanted to mount a particular version of the Linux operating system into my EC2 instance for me. I really don't want to get into this too much because we're not going to be using EC2 at all after this week. So that's why I'm kind of skirting around it a little bit. So the net effect of this piece of infrastructure code is that an EC2 instance will be created for me in my account, in my AWS account, and there'll be some other resources created as well. Like it will create a firewall or a security group around that instance. It'll create an IAM role. So it'll create some other resources as well. And those resources um, are created automatically for me because I'm using this L2 construct in my infrastructure code. And that's, again, another example of the benefit of using the CDK as opposed to writing raw CloudFormation. Because if I was using raw CloudFormation, I'd have to be explicit about all those other resources that I needed. That's my stack. Here's the app, I suppose you call it. And there's very little code, as I said. All you do inside in the bin file is you create an app, CDK app. You create an instance of the stack. So that's a reference to the and creating an instance of the class that I was talking about there a few moments ago. Creating an instance of it. I'm linking it to my app instance that I've created up here. And I'm giving a name to my stack. And I'm just being safe here, but you kind of get away with it. Sometimes, sorry, you get away with not needing to do this, but all I'm doing here is I'm telling it what region I want the stack to be deployed in, because you do have to tell it what region, but it often can pick up the region from whatever your AWS CLI settings are, which you would have done, last week. And this is my AWS account number. So I'm being explicit, but the CDK can pick up those two values from my AWS CLI configuration. Now, I have already, so to run this app, in other words, to deploy it, you just submit the CDK deploy command from the base folder. Now, I did that before class. And so if I go over to the CloudFormation service first, I can see evidence that my app has deployed because this stack here, this stack corresponds to the stack name that I wanted to use. So I kind of have confirmation there that because my app only comprises of one stack, that my app seems to have deployed successfully because I can see my stack there. And, you can see here that this confirmation that the stack was created. But in terms of the resources, I'm particularly interested in the EC2 instance. So if I go over to the EC2 service, and click on instances on the left, and here's the instance that was created for me by CloudFormation. Now, and you can see the instance has an IP address. Now, obviously what I'd like to be able to do maybe is to connect to this EC2 instance using, let's say, SSH. But by default, I cannot do that. What I need to do is I need to open up the particular TCP port 22, on this server instance, or this VM instance, open up port 22 so that I can connect to it remotely. But by default, that port is not open. And the way I can prove to you that the port is not open is, as well as creating that EC2 instance, if I click on the security tab here, for each instance that's created, the AWS also has this notion of security groups, and a security group is essentially a firewall around an EC2 instance. So a firewall has been created for my EC2 instance, but by default, this firewall's configuration is very limited. And am I looking at it here now? Sorry. Here's the if I click on this here, it'll take me to the security group / firewall that has been created for my EC2 instance. And in terms of the configuration of that firewall, I can see if I look at the inbound rules associated with the firewall, there are no inbound rules, which means I cannot access any of the ports in my EC2 instance. There are some outbound rules, which is essentially saying that the EC2 instance itself, the Linux server, it can make outwardly requests, okay, but I cannot make an inward request to it. So how do I fix that? Well, I need to change the configuration of my security group, which brings me back to my code. And so I've got that here. I'm just going to, and I want to bring this code. Obviously, I want to enable it, but because it's going to be referred to from my EC2 configuration, I need to bring it up before it. Usually, the ordering of the resource of the constructs in your stack are not important unless one construct refers to another one, and that is the case in this instance. So what I'm doing here is I am creating a security group for myself. This is another example of an L2 construct. I'm linking the security group with the current stack, giving the security group just a name, although that's only going to be part of the name. The AWS will also add a hash, add a hash value to the name, so to make the security group unique within the region. And here's the configuration for my security group. But also I am adding some more configuration here. And in this part that I'm adding on, you can see what I'm trying to do is I'm trying to enable port 22 in my security group, which will mean that I will also be able to access port 22 on my EC2 server. But all I've done here now is I've just created a security group. I now need to link this security group to my EC2 instance. And so that means change my EC2 configuration. And you see the benefit of TypeScript here now, because if I start typing here, TypeScript is telling me maybe this is the property that you want to set. And so I just need to refer to server, what did I call it? Server SG. So I've now changed my stack. I've changed my infrastructure configuration. I've added some resources and I've changed the EC2's state, if you like. So in order for this to be applied, I just need to go CDK deploy again. So if I hit deploy, CDK deploy, then as I said, it will create a new version of the template. And you can see the templates, even though you don't need to, but the templates are stored inside the CDK out folder. And so here's the template itself in JSON. But as I said, unless you're doing something very intricate, you really rarely need to go looking at that. But let's do CDK deploy. And if any changes have potential security implications, and you're always asked by the CDK framework, are you happy for this to continue? So we'll say yes. And while it's working now, if I go back to the management console, which is my web interface, to my resources, and if I It doesn't actually, it does not update the current security group. In this case anyway, it actually creates a new security group, a new resource. Often it modifies existing resources, but in the case of security groups, which is kind of one of the odd one out cases, it actually creates a new one. So I need to go back to my instance. I'm going to do a manual refresh, check to see if it's completed. So that's done. And again, now if I select my EC2 instance, select the security tab, find the security group. And if we look at the inbound rules now, we can see that it has added a new inbound rule, as it's called, and the inbound rule relates to sorry, am I looking at the right one? I'm just going to do a manual refresh here because I think it's looking at the old page.
I think you can scroll down in the left-hand side pane to check out the security groups.
Uh, Sorry, say that again.
The left-hand side pane is there, right? The navigation pane. I think you can
Oh,
scroll down to view
yeah,
the.
you can get them there as well, but that'll show me all of my security groups, and there are probably ones hanging around there that I'm not interested in. But um, and why am I not? Oh yeah, so here I am. I'm looking at the inbound rules, and you can now see that there's a new inbound rule added here, and it relates to port TCP port 22. So that now opened up. And just to complete the picture again, maybe only for those people that aren't familiar with any of this stuff, if I go back to that, now means that I can make an SSH request to the CC2 instance. So I need the IP address of the instance, and I can get that from here. Here's the public IP. So if I copy that and just quickly do an SSH request. Again, for those of you that haven't done any of this stuff, by default, the EC2 instance will have a user called EC2 user configured in it. And so that's why I'm making an SSH to EC2 user at this IP address. I'll explain what this is in a second. If I just make the call first, though. Right, so I've now SSH'd to my remote server, and I can do whatever I wanted. Typically, it would be install some software, start up some servers and this kind of stuff. Again, for the benefit of those that haven't done any of this stuff before, here, because I'm making an SSH connection, obviously it has to be secure. So I need my connection to be encrypted, and I'm encrypting it using what's called a key pair. And this key pair is generated by the EC2 service itself. Now, and I have downloaded the key pair in the form of a PEM file. How do I generate this key pair? If you go back to the EC2 console, you'll see down here. I'm not really too concerned with showing you this in detail because we're not going to be using EC2 after this week, but you can see key pair there. And you can just create a key pair and it will create a public-private key combination, and it allows you to download your key pair. And that's what I did earlier on. So, and then use that key pair in my connection. And also you might have noticed, or sorry, if I go back, the key pair that I used, I've called it EC2 CDK. That's just the name I gave to it. And you can see in my infrastructure code, I specified that I was going to be using that particular key pair in the configuration so that the communication worked essentially. Right. So that's our first look at the CDK framework. And so in this week's lab, linked to that, which is this one here, before you can use the CDK in your account, you have to, what's termed, you have to bootstrap your account. And so I'm explaining here in the first part of the lab, the bootstrapping process, pretty straightforward. And once you've done that, then you can use the CDK framework, but you do have to bootstrap, and you have to bootstrap your, if you are going to be using the CDK in multiple regions, which you won't have to for this module, but if you did want to for some other reason, then you have to bootstrap your account for every region. And then in the lab, what you'll be doing, you're actually going to be creating quite a sophisticated infrastructure. I'm not, again, for the benefit of those people who did not do the cloud architecture module in the first semester, this infrastructure is a bit overwhelming for those who did do it. Then you will be able to make sense of the infrastructure there or thereabouts. So I've got a couple of EC2 instances, I've got a security group, I've got an auto scaling group, I've got a load balancer. So there's a lot going on, but I don't really need those of you that haven't done the first semester module to be fully comfortable with all of this infrastructure. Just walk your way through the lab, and as long as the lab works, then I'm happy that the CDK framework is now properly installed locally and remotely for you. But the lab should still make a certain amount of sense, even though we are using resources. We're using infrastructure resources that I haven't talked about at all formally. I haven't talked about an application load balancer. I haven't talked about an auto scaling group. And nor am I, because I don't have time to do it, but you can walk your way through the lab anyway. And you can ask me questions in the lab if you have some detail about understanding this infrastructure. But I am not too concerned with you needing to be fully clear on the infrastructure, because we won't be using EC2 at all after this week. I'll pause for a second in case there are any questions. Now, where we want to go though really with the CDK is we want to move into the serverless world of cloud computing, and we want to create serverless oriented infrastructure. So that's where I'm going to go next. And I'm going to work my way through some of these slides, and just in the background, I am going to destroy the stack, because I do want this to be as inexpensive as possible for you. And certainly one thing that is not inexpensive is to have EC2 instances up and running. So I'm going to CDK destroy. So this is going to essentially send a request to the CloudFormation service, telling it to send a request to each of the individual services that did create a resource linked to this app and asking that service to delete that resource. There are other resources as well that I haven't looked at, like there was an IAM role created linked to my EC2 instance, but and so I'll let CloudFormation take care of all of that. And you should check if you ever do get an error when you try and do a CDK destroy, and there are rare occasions that it will happen, then what you should do is go straight into CloudFormation and delete the stack from there. Okay, so we'll assume everything is going to work out fine. Now I'm going to have to stop sharing my screen for 1 second while I switch these slide sets. So I've titled this serverless web APIs because serverless can apply to any type of server-side application, but we are going to be using it specifically for developing a web API. So that's the only reason I've tagged on web API to this. But the main thrust of this section is serverless for today anyway. Okay, and so again, see, some of you have come across serverless formally on this course in the previous semester, some of you haven't, but just very quickly, what the implication of using a serverless approach towards I suppose the infrastructure that you want to use for your server-side application is that you as a developer, you are not concerned with provisioning your server instances, just as we were there in the demo. So we don't want to be lumbered with provisioning EC2 instances and configuring them and managing them and making sure they're always up and running. Now I know auto scaling groups can take care of some of that stuff for you, but a serverless relieves the developer, I'm saying here, of having to just provision servers at all. Servers are still being used, but it's just that we as developers don't need to concern ourselves with them. Also, as a developer, you don't need to worry about scalability of your server-side functionality. The serverless services that we will use will take care of scalability. By scalability, we simply mean that if there is a high volume of activity targeting your application, like requests coming into your server-side application. If there's a very high volume or a peak in the volume of requests hitting your application, then you'd like your application to scale up and deal with that volume. In other words, you would not like your application to suddenly become heavily latent in the responses that it's sending back to the requests that are targeting your application. You'd like the application to scale up accordingly and then scale back down once the peak starts to decrease. In the server-oriented world, this is something we had to be concerned with, and we had to configure it ourselves. Whereas in the serverless world, you let the platform take care of scalability. Number 3, upfront costs. Well, in the server-oriented world, as long as you've got an EC2 instance, which is a server, as long as that's up and running, you're paying for it, even though it may not be being used. You're still paying for it. Whereas in the serverless world, you only pay for however many requests are hitting your application. Availability is another thing. You always, in the server-oriented world, you have to make sure that your servers are always up and running. And if they crash, then you've got to make sure that they are rebooted and all of that stuff. Now, again, you can automate a lot of that, but you do have to automate the rebooting, etc. Whereas in the serverless world, again, that's kind of taken care of for you. I'm not getting into the detail of the how of these things because we don't have time for that stuff, unfortunately. Web APIs, I guess, hopefully everybody should know what a web API is, but I just said I'd cover it anyway. So web API is, I'm saying here there's some functionality running on the server, on the server side, whether it be on a serverless platform or on a server oriented platform. It's some functionality running on the server side. That functionality has got some sort of interface to the outside world. In other words, it can be connected to via HTTP. And your client can be anything, okay? In our case, in this module, our client will be a web client, but all of the other are possible clients as well. And really the functionality typically doesn't care about the nature of the client. All it's getting is HTTP requests. So that's a very kind of high level statement of what a web API is. Now, in the Amazon world, it has many serverless services, and I'm listing some of them on the left, and we'll only get to look at a small subset of them. So, for example, AWS Lambda is a compute service. In other words, it's an alternative to EC2. And we've got some other ones as well. I'm not going to go through them. On the right here, on the right really is, in a sense, by accident rather than by design, it's a snapshot of what we would like to achieve by the end of this module. And so let's just talk about the picture a little bit. What we'd like to have is our functionality of our web API implemented as Lambda functions, these things down here. So there will be many of those, okay? There'll be a Lambda function for each part of our functionality, let's say. And these Lambda functions will be accessed externally. If you go back to the previous slide where I had clients talking to my functionality, well, it's not going to be talking, my clients aren't going to be communicating with the Lambdas directly. They're going to be communicating with the Lambdas via what's called an API gateway. An API gateway is another one of it's mentioned there on the left. It's another one of AWS's serverless services, and it's specifically for developing web APIs on the server side. So requests are going to hit your API gateway first, and the API gateway will be configured so that it knows which of these Lambda functions it should send the request to, and the Lambda function does its thing. In many cases, the Lambda function will be interacting with a database. Our database is going to be implemented using the DynamoDB service. The DynamoDB service is one of AWS's serverless database services. There are others though. On the right here, we're using something called AWS Cognito. And AWS Cognito is AWS's serverless service for managing user authentication. So typically, a login will target the Cognito service and it will take care of authenticating the login request. And typically what it does is it returns some sort of a token, specifically a JWT token, and that token then is used by the client for making subsequent requests to your particular lambdas, so that only clients that are authenticated can actually trigger the execution of a lambda. On the left, I have an S3 bucket. S3 is Amazon's object storage as opposed to a database. It's an object storage service, file service, you could typically regard it as. But we can use, or one can use the S3 service to host a website or a web app. Now, in the second half of this module, you will be developing a web app, which is your client app, and hopefully we'll get time to deploy that into an S3 bucket. And S3 is also serverless, although it predates serverless, but it is a serverless service. There are servers being used here, but we don't configure them. And so our entire infrastructure is serverless, and that's what we hope to achieve. But we've got a long way to go before we can get to there. So what I want to do is talk about some of the individual services that we need to use in order to achieve that infrastructure that I showed you on the previous slide. And the first one is AWS Lambda. And again, as I keep saying, some of you will have done some stuff on AWS Lambda in the previous semester. Some of you haven't. So for those of you that have, sorry about this slide. So what is AWS Lambda? It's an event-driven serverless compute platform. So computing means it's where you can have functionality deployed to, code, in other words. Serverless, we know what that kind of means now. Even though it's running code on the server side, we don't have to worry about the platform that code is running on. The AWS was going to take care of that. Event-driven means that it's some sort of event that will trigger the execution of our functionality, as opposed to, command line driven or user driven. It's some sort of event driven. And the AWS Lambda service is going to manage the what we deploy to the AWS Lambda service is an AWS Lambda function. And it's a function in the traditional sense of a function. We were developing TypeScript functions earlier in the module. So we can actually deploy something as small as a TypeScript function. We can deploy that in isolation to the AWS cloud. Like pre-serverless, what we deployed was an entire application, typically on top into an EC2 instance. But now we can deploy a small part of an application, one function, in isolation. And we use the AWS service to do that. So what we deploy is an AWS Lambda function. And that function has to be, when it does need to execute, in other words, when the event that occurs that triggers the execution of our function, then what actually happens behind the scenes is the AWS service, it creates an instance of what's called a micro VM instance. And it runs that micro VM on one of its many servers. And having created the micro VM instance, it loads the appropriate operating system into that instance that will be controllable by your infrastructure code. And then it loads the actual AWS Lambda function into that micro VM instance. And then it executes your function and passes it the event that triggered that whole process. And if there are no other events immediately following that event, then it simply throws away the micro VM instance. It trashes it until another event occurs that's targeting your function, and it goes through the same process again, creates another micro VM instance, loads up the relevant operating system, and loads your function into it, passes the event to it, and executes the Lambda function. Now, it probably holds on to the micro VM instances for a while in case there are subsequent requests. Doesn't want to have to go through that long initialization process every single time if it can avoid it. So it does warehouse, if you like, these micro VM instances for a short period, though. Obviously can't hold on to them for too long a period. So that's kind of what happens behind the scenes. So what I'm saying here is that this whole Lambda service, what it's all about is it's about custom code, which is the AWS Lambda function that you write, custom code that runs in an ephemeral container. The ephemeral container is this micro VM instance that I was talking about. Ephemeral essentially means that it kind of creates an instance of the container, the micro VM, and it just throws it away if it doesn't need it shortly after having created it. Another term for this whole area is FaaS, or function as a service. So then this again kind of describes what a typical serverless application at a very, very high level kind of looks like. So here is the Lambda function that we write. The execution of that function is managed by the AWS service, AWS Lambda service. And so the event that triggers the execution of your Lambda function, that event is first of all grabbed by the AWS Lambda service. And based on your infrastructure code, it knows, well, this event needs to be passed to this particular Lambda function. And it passes the event to the Lambda function, and the function does its thing. And, you know, the function can do anything, include possibly talking to other AWS services. So this could be DynamoDB service or the SQS service or whatever. So the key kind of parts to this diagram is the event source. So the whatever caused the event to occur, that's what we refer to as the event source. And the event source can be anything really. It could be an external HTTP request, which it will be in the case of a lot of our web APIs. Could be HTTP request, as I'm saying down here. Or it could be a change in a data store state. So the data store could be a DynamoDB database. So if you can imagine you had a DynamoDB database here, and there was a new record added to that database. The addition of that record caused DynamoDB to fire an event, as we say. And that event is what is triggering the execution of our Lambda. Or you might imagine an S3 bucket over here, or file storage service. And whenever a file is uploaded to the S3 bucket, that causes S3 to fire an event. And that event is what triggers the execution of our Lambda function. And the firing of the event and the link between the S3 and the execution of this Lambda function, you have to describe that in your infrastructure code. And hopefully we'll get to, we won't actually, as it turns out, but not in this module. In another module, I do that. But anyway, in our case, it'll be always HTTP requests. That will be the source of the event for triggering our Lambda function. The Lambda function can be written in any language, pretty much any language that you wanted, those that are supported by the AWS Lambda service, and that's a growing number of languages. We are going to be writing our Lambda functions in TypeScript, but you can write them in other languages. And in fact, within one application, within one stack, you could have a number of Lambda functions, and they are using different source code languages. So you could have a Python Lambda, TypeScript Lambda, a Go Lambda, all within one stack, because the Lambdas are completely independent of each other. So you pick the language that's most suited to the nature of the processing that's done by the Lambda in general, but we'll be using TypeScript in all cases. There's some general stuff here about the Lambda service. It takes care of auto scaling. If I just briefly go back to this one, let's supposing there's a high volume of these events concurrently happening. What the Lambda service does is it'll actually create multiple micro VMs, and each one is going to be running its own copy of the Lambda function. And the Lambda service will distribute the events between the various micro VMs, or between the various running instances of your Lambda function. So it scales up automatically, does that automatically for you. Now, there is an upper limit to how many parallel micro VMs, and you can control that to a degree. But that's how it deals with scalability. And it just gets rid of these micro VMs then as the volume of events start to decrease on the left. So it takes care of auto scaling, takes care of load balancing between those multiple micro VMs that are running in parallel. It takes care of the managing the operating system that's running within each micro VM. It makes sure, you know, that okay, you might have multiple micro VMs, concurrent micro VMs, all running the same Lambda, and they may actually even be running on the same hardware piece hardware, but the Lambda service will ensure that each execution of your Lambda function is completely insulated from the other running executions, as you would want it to be. And finally, and most importantly, I suppose, the Lambda service will take care of providing the necessary utilities that the function needs. And by utilities, we mean the CPU power that it needs, the RAM memory that it needs, and the network bandwidth that it needs. The Lambda service takes care of provisioning those at runtime for your Lambda function. On the right, I'm saying that the characteristics of this AWS Lambda functions approach is that, you know, a function now is the unit of what I'm saying is the unit of scalability, as I was kind of describing there a moment ago. Whereas previously, scalability happened at the application level. You had multiple copies of your application running on multiple EC2 instances. That's how you scaled up and scaled down. Whereas now you scale up at the function level. So it's far more fine-grained. Number two, your function is the unit of deployment, whereas previously the unit of deployment was your entire application. But now you can essentially deploy particular part of the application in isolation from other parts of the application. Thirdly, well, the stateless nature, clearly, if you've got your Lambda function running inside the micro VM, and you know, it's obvious, I suppose, but if it throws away the micro VM and another event occurs, the next execution of your Lambda function has no knowledge of the previous execution of the Lambda function. Obviously, I guess, you know, but so that's what we mean by stateless. Whereas that was not the case in the pre-serverless world. You could have some sort of history, and that might be beneficial. Okay, if you want to simulate that in the serverless world, you've got to approach it another way. There is there's a limit to how big your Lambda function can be in terms of how much processing it can do when it's executed. And I think the upper limit, although it might have increased, but initially anyway, the upper limit was it could not run for over the max was, I think, 15 minutes. So if it was really heavy processing that took more than 15 minutes to complete, then you could not use the Lambda service as a way of implementing that piece of functionality. What you would tend to do is implement that type of functionality, not so much as a separate application running on EC2, but you might run it as a Docker container running on, let's say, something like AWS Fargate, which is a serverless container service. Also, the pay per execution characteristic, you only pay as the user of the AWS cloud, you only pay for how many times your Lambda function executes. Whereas in the server-oriented world, you were paying for your EC2 instances, whether it was running and handling any requests or not. So Lambda function, in terms of the code that you write, this is what it looks like. It's the anatomy I'm saying of a Lambda function. There's the actual function itself. You can call it anything, but conventionally we refer to the function, we name it handler. So handler is my Lambda function. You also have what's called initialization code, and in the initialization code, which is outside of your handler function, that is where you put typically things like database connections. So if you have to connect to a database, inside here, you would be doing your reading and writing to the database, but to actually get the database connection, you do that outside of the handler. Or if you were communicating with other services like SQS, the connection you make to the other services, that code should be put. It doesn't have to be, but it's bad practice if you don't put it outside the handler. And I'll explain later on why that's the case. Or do I do kind of mention it here? The handler itself, clearly it's an asynchronous function because it's being invoked over the network. Everything is happening over a network in the cloud, of course. The handler function takes two parameters, but really the first one is the one that we use mainly. We don't tend to use the second one. And based on the name, the first parameter that will contain all of the information about the event that triggered the execution of your Lambda function. Typically would contain some important data that the function then uses as part of its processing. The context really more relates to if you want to drill down into the runtime environment and you want to get access to some part of the runtime environment. In other words, the micro VM itself, but that's rare, and we never need to do that. At the bottom here, I'm saying the initialization code executes before the handler. Okay, for cold starts. Like what actually happens when you're when the Lambda service creates this micro VM instance, what it does is it executes the initialization code and then it executes the handler. And let's supposing there is another occurrence of the event immediately after, and it decides that it's going to use the same micro VM to process the subsequent event. Well, the processing of the subsequent event, it does not need to run the initialization code this time because that has already been executed by the micro VM. It's made the connections to the external services. So we don't need to do that again. And that is quite expensive from a time and latency point of view. But for the subsequent event, provided we're using the same micro VM instance, the initialization code is not executed, only the handler is executed. And so we get the benefit of not incurring the latency associated with the initialization code. When it does have to run the initialization code, we refer to that as a cold start of the micro VM. When it does not have to run the initialization code, we refer to that as a warm start of the micro VM. And I'm mentioning those two terms down at the bottom. So your Lambda is a compute service, and so it's going to consume CPU power. It's going to need some RAM memory. It's going to need some network bandwidth potentially. And it needs those three utilities, and we can configure those utilities in terms of how much of each of them do we need for our Lambda function, because it's going to vary from function to function depending on what processing the function does. Now, rather than allowing the developer to configure each of those three parts of the Lambda functions configuration, what the AWS team decided was they would just allow you to configure the amount of RAM that your Lambda function needed. And then based on that, the Lambda service itself would compute how much CPU power it should provision for your Lambda function and how much network bandwidth. So this was a conscious decision made by the AWS team. Rather than giving the developer too much control over the utilities that your Lambda function needed and potentially, configure them incorrectly, it just gives the developer one dial that the developer can control. So it's the RAM dial. So the more RAM that you allocate to your Lambda function as part of its configuration, that determines how much virtual CPU power will be provided for the running of your Lambda function at runtime, and also how much network bandwidth. And I'm explaining on this slide, well, not explaining, I suppose, but outlining on this slide how we configure the RAM. So it's the smallest amount of RAM that you can allocate is 128 megs, and it can be up to a max of 3 gigs, which is pretty significant, as you might imagine. And I don't really want to get into this because we're not going to be concerning ourselves with this sort of fine-grained configuration of our Lambda functions. Obviously, it is important because the more RAM that you ask the AWS cloud to provision for your Lambda function, the costlier it is to run your Lambda function. Okay, quick demo. A very quick demo. Let's see. Close that off. So it's a CDK app again, and let's get straight to the important part, which is my stack file, which is here. And my infrastructure comprises of one thing, again, for simplicity's sake. And in this case, we are creating a Node.js function construct instance. So Node.js is another L2 construct. And it's part of the Lambda, part of the AWS library. And again, I need to link my Lambda function with a stack. So I'm linking it to the current stack. I just give some sort of name to my Lambda function, and the rest then is the configuration for my Lambda function. And for this particular case, although it's not important, I'm saying I want ARM24 architecture. I want it to run on a particular type of hardware. I mean, it doesn't really need to. This one makes it a little bit more sense to us. I want my micro VM to have Node version 18 installed on it. Here I'm just specifying the actual where my Lambda function is implemented, which is here. Look at that in a second. And here I'm saying, I'm telling the Lambda service that if my Lambda function runs for more than 10 seconds, then it should essentially destroy, it should interrupt the micro VM and cause an exception and send back the exception response back to whoever triggered the execution of the Lambda function. Note, I'm not specifying any RAM memory here. I'm accepting the default. And the default is the minimum, which is 128 meg, and that's fine for what this particular Lambda function does. So there's very little configuration there. And that's about it, really. The only other thing I'm outputting, the only other thing I'm including in this stack is here. And sometimes you want to output some information back to the terminal when you do a CDK deploy. In this case, I want to output the full name that the Lambda service assigns to my Lambda function. The name will comprise of the stack name, the name that I specified here, plus a hash value. So it'll be some long kind of string. And I do want that to be output to the terminal because I'm going to be invoking the Lambda function using the CLI. But that's it, right? Now, my stack file, nothing interesting in there. Sorry, my app file, nothing interesting in there. Again, I'm just creating an empty CDK app, and I'm creating an instance of my stack, which I've just shown you, and I've attached it to my app. So that's it. If I do CDK deploy, and if I switch over to the Lambda service, so it's still deploying. Okay, now it's done. And I also have there's the name, the full name of my Lambda function. And this line was generated by this statement in my infrastructure code. And if I flip over to the management console and just go to functions, do refresh. There's my function. And the function name corresponds to what I saw on the terminal there. Now, the only way I can trigger this function is by using the CLI. So my CLI command is going to look like this. And if I just substitute in the name of the function, now I didn't look at the function, but let's quickly look at it. Pretty uninteresting. Here is the implementation of my Lambda function. And it does nothing other than it does a console log and it returns this response. Yeah, that's all it does. So if I run it, now when you run it using the CLI, the response that comes back from the Lambda service, you have to put that into a JSON file locally. And so I'm just saying, put the response into a file called response.json. And so I ran it earlier on, so I'm just going to delete that for now. You would overwrite it anyway, but okay, so we're good to go. This is just coming back from the lab. This is just coming back from the AWS, sorry, from the Lambda server saying, look, everything was okay, but the actual response from the Lambda function is inside in my response.json file. And so if I open that up, and surprise, surprise, if you scan it across, that is consistent with the code that I showed you. So this kind of message, for example, that's consistent with what my code was actually saying it should return back. The console log, this is the last thing I'll cover with you. The console log, where does that go? Because we will be using console log quite a lot, mainly as a kind of debugging aid. It's pretty primitive, I know, but where do console logs go? Where can you see them, the output from them in the cloud? And the answer is there is a service called the CloudWatch service. The CloudWatch service is used by many other services, including Lambda. So if I go over to the CloudWatch service, and if you select log groups, there will be a log group for each Lambda in your serverless application. There would also be log groups for the other services that use CloudWatch. Won't arise, I don't think, in our case, but it will mainly be the Lambda service that will be using CloudWatch. The log group names are constructed by CloudWatch itself, and the name is kind of indicates which service this log group belongs to. So you can see from the name of this log group that it's coming from the AWS Lambda service, and the rest of the log group name is specific to our Lambda function. So it's a kind of contains a bit of the stack name and the actual function name. So if I click on that log group, a log group is comprised of log streams. And in the case of a Lambda function, there'll be a log stream for every execution of your Lambda function, there or thereabouts. If there are two or three, if there are a number of quick consecutive executions of your Lambda function, then they'll all be packed into one log stream. But not in our case. We only had one execution, so there's one log stream down here at the bottom. And if I click on that, now I can look at the detail of the log stream. And in particular, if I pick out this part of the stream, where is it? Is it here? Let's see. Oh yeah, there it is there. So that there, I was invoked. That's consistent with what my console log statement wanted to output. And as I said, you'll be using console log as a debugging aid, really. As I said, it's quite primitive, but there are more sophisticated ways of debugging lambda functions, but we just don't have time to look at the more sophisticated ways, as it turns out. So we'll just have to use console log instead. So that's our first example, very simple example of using the CDK to deploy a serverless app. Now, calling it an app is a gross exaggeration because it just consists of one lambda. But you have enough information to go to the lab associated with this section, and you will be able to complete the first part of the lab, which is this part here, standalone lambda functions. From there on in, then I need to cover some more stuff before we can do the rest of this lab. Okay, we're out of time. I will take any questions in case there are any that you might have. Happy to go on for a while longer if you want to, but are there any questions, I wonder? No. Okay. Now, next Monday is a bank holiday, as you may know, so hopefully I'll have a pre-recorded lecture because we can't really afford to lose a week in this module, but I'll try and put together a pre-recorded lecture and release it at some stage early next week for you. Right, that's it. Thanks for tuning in. Talk to you on Thursday. Bye-bye.